Welcome back to Arxflix. Today, we're diving deep into an intriguing new paper titled Learning Fine-Grained by Manual Manipulation with Low-Cost Hardware. This research tackles the challenge of executing precise manipulation tasks, such as threading cable ties or slotting batteries, using low-cost hardware. Let's get into it. Unlike high-end robot systems, which require expensive sensors and careful calibration, this study explores whether learning can enable affordable and imprecise hardware to perform such tasks. Here's a view of the system setup. The left image shows camera viewpoints, middle details the custom grippers, and the right offers technical specs of the ViperX 6DoF robot. But how does this low-cost system achieve such precision? Let's break it down. Traditional systems for fine manipulation rely on high-end robots and precise state estimation from advanced sensors. These setups are costly and less accessible. Instead, the authors propose a low-cost approach using learning techniques. Inspired by how humans perform delicate tasks despite not having industrial-grade proprioception, they train an end-to-end policy that directly maps RGB images from commodity webcams to actions. This approach simplifies the manipulation policy by using closed-loop feedback to handle interactions with complex physical properties, bypassing the need for detailed modeling of the environment. Training an end-to-end policy has its own challenges. The policy's performance is highly dependent on the quality of training data. The authors mitigate these issues with high-quality human demonstrations and a novel imitation learning algorithm. Check out Figure 2. Which illustrates the action chunking with transformers, ACT, architecture. The encoder compresses action sequence and joint observation into a style variable, Z, while the decoder predicts a sequence of actions using RGB images and joint positions. The proposed system has two main components, a teleoperation system and an imitation learning algorithm. The teleoperation setup uses off-the-shelf, low-cost robot arms and 3D printed components. This system enables teleoperation tasks such as threading a zip tie or juggling a ping-pong ball with around a 20K budget. On the imitation learning side, fine manipulation tasks pose a significant challenge due to errors compounding over time. Inspired by action chunking, the authors group sequences of actions into chunks and execute them as single units. This reduces the effective horizon of the task and mitigates compounding errors. By predicting action sequences, pi theta, a t, TKSD, instead of single actions, and averaging across overlapping chunks, the policy ensures smooth and precise motion. Figure 3 visualizes how action chunking helps in reducing compounding errors and smoothing transitions in actions. The results speak for themselves. The system successfully learned 6 difficult tasks, like opening a translucent condiment cup and slotting a battery, achieving a success rate between 80 to 90% with just 10 minutes of demonstration data. This success is a significant step forward in making fine-grained robotic manipulation accessible and affordable, which could revolutionize various practical applications. Figure 4 shows real-world task definitions, highlighting the initializations and subtasks. The paper compares the ACT method with 4 other imitation learning baselines. The results show that ACT outperforms all competitors by a large margin, proving the effectiveness of action chunking and temporal ensembling. As shown in Figure 6, ACT significantly benefits from action chunking. Adding temporal ensembling also improves performance, ensuring precise and smooth action sequences. This study presents a novel approach to fine manipulation with low-cost hardware. The synergy between a high-performance teleoperation system and the ACT algorithm demonstrates impressive capabilities, making precise robotic manipulation more accessible. Despite its success, some tasks still remain challenging for the system, such as buttoning a shirt or unwrapping candies. The paper emphasizes that improving perception and increasing data could help overcome these limitations. Overall, this research is a critical step towards democratizing robotic manipulation. If you're interested in more details, check out the project website linked in the description. Thank you for watching. Don't forget to like, comment, and subscribe to Arxflix for more research summaries like this one. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.